All right, so we're here today with Brandon Bray, who is a C++ guru. Many people are aware of your blog, etc. So let's start off. I mean, we're going to dig into the new changes for the new version of C++ and the evolution of C++, future, etc. But let's talk a little bit about your history and what you do on this team.
Okay. I actually started 5 years ago, and I was originally on the compiler code generation team.
Okay.
And I had the opportunity to first start on security. I did a lot of the GS architecture for the 2003 release and 2005. So about 9 or 10 months after I started, I switched over to the compiler team, and it was actually quite a shock for me. I only really learned C++ 4 years ago.
Wow.
So, kind of a rapid learner.
Seems like it.
But one thing that I was very passionate about when I started in Visual Studio was language design. I was quite impressed with C#, but there was another project at Microsoft that really pulled me to Microsoft, and that was the Intentional Programming Project. So at the time, the team didn't have headcount, for me to join, but I wanted to stick around. Fortunately, the Intentional Programming Project kind of fizzled away while I was still in college, and but my passion for language design stuck around. And
Excellent.
I stuck with it, and I think I've certainly learned a great deal by working on C++. There's this essence of what does it take to make a successful language, and I think in my college days I never really had to think about that. It was just what was fun.
But let's answer that question. So what does it take to build a successful language? And certainly C++ is a successful language.
I think it's largely compatibility, and it's surprising. C++ was compatible with C.
Yeah.
And the evolution of C++ and C have been largely about compatibility. And they try to if they make changes that break compatibility, they make them in very careful ways, so that upgrades can be made. And that also goes to the success of any new version of Visual C++. We saw that switching from VC6 to VC7, had a lot of changes in MFC, and then going to the Visual C++ 2003 release, which was our conformance release, had dozens of breaking changes to introduce compatibility.
Okay.
But how we focus on that, or compatibility with the standard, I should have said, really is important. When we make a breaking change, we need to make it very clear that this is a point where something is changing, that we don't silently break things, and that we give people a migration path. So that's kind of the one thing that we have to think about in total, is people don't want to rewrite everything.
Absolutely. So now, in 2003, you guys introduced the notion of writing managed C++ to take advantage of the great CLR.
Right.
And since the CLR is language agnostic, you could care less what language as long as you're CLI compliant.
That's right.
You guys decided to add some extensions so that C++ people could write, have some managed code. Didn't work out that great. You learned from what customers wanted. I mean, it was a hard problem to solve. But anyway, to cut to the chase, you've done some great stuff for VC 2005. I guess that's what you're calling it. Can you talk a little bit about the challenges of making something like C++ conformant to management in the CLR world?
Sure. So one thing that we really had this struggle with, and what was our audience for the new language, and it goes back to ISV customers need to have a way to use C++ in their existing applications that have a long history, and we're creating a lot of these new libraries that have innovative new approaches, like presentations and communications. And if we don't provide that ability to integrate those libraries into their existing applications, they'll never use those libraries. And that leads to a less successful library.
Okay.
So one thing that we really wanted to make sure is that every aspect of the CLR that's required to use those libraries can be accessed from the C++ language. And the mapping between some of these new ideas have no exact match in the C++ language. So, for instance, the security system in the CLR is based on going through and doing stack walks and demands to make sure that does the caller of this function or this library have permission to call this. And if you read the C++ standard, it has no concept of anything beyond the program itself. It's simply looking at, we're looking at, here's a library that you might be using, and a library to the C++ standard is just something that gets compiled into my program, and so I have full control over changing that library. And so like DLLs just don't come into play in the C++ standard.
Okay.
So we're facing like just things that aren't mentioned in the C++ standard, and really trying to fit that in with an appropriate language approach. And most of the languages that already compile to the CLR use this notion of attributes to like declaratively state as I have permission to call this API, or to assert that permission, or maybe they want to demand that permission also.
Okay.
And that leads to we have to provide some way to declaratively say that. So that just goes into we needed a way to add attributes to the language, which just aren't there.
Absolutely.
Today.
Yeah. So, what have you done in the new language specifically that makes it easy for a C++ developer to call into a managed API?
Okay. There's one really simple thing that we did, was that we added a new declarator, basically, where if I wanted to have some type that was garbage collected, since everything on this CLR is garbage collected, you needed some way of representing an object of that. So we added this thing called a handle, and represented by a caret, or what we often call a hat.
Okay.
So when you have that hat, you just do t hat t, and then you can garbage collect it by saying gc new that type, and effectively it's a parallel to just saying t star t is equal to new of some other type.
Okay.
So when you say new, it allocates it on the process heap instead of the garbage collected heap, and gc new garbage collects it. Okay. So that one thing is kind of the center point between all of the access to the libraries. So
excellent.
To say we wanted to get to something in the drawing APIs, all we'd have to do is write pound using system drawing .dll, and that is effectively the same as including a header file that's associated with that DLL. And the DLL itself describes all of the types that it supports, and functions, and enumerations, and so forth. So just by writing pound using on that, I get all of the access to the drawing APIs, and so I can then go into the namespaces for each of the drawing APIs, you get the type, and gc new them. And so when I write something like gc new of some type, and then I can start accessing functions, I can do that inside of my existing functions and that I have in native classes. So it leads to a very organic approach of, I just need to use this API, so I want to start using it.
So now, C# has the handy-dandy using keyword, right, which guarantees that the object will go out of scope. In other words, you don't have to explicitly kill it, which really you can't do anyway. Well, you can, but... So in C++, what's the metaphor for that? I mean, what would I do if I had to if T inherited from some sort of stream class and had to be closed?
Right. So fortunately for C++ developers, this isn't all that surprising. What we're thinking of, what basically you're describing is the original idea that Strustrup presented in C++ with object-oriented encapsulation. So when you have a class that is a file, you want to use that file. When you're finished using the file, you want to call the destructor for a file, and that destructor needs to close something.
Okay.
So effectively, that makes things very simple. That you're getting rid of when I start using a file. In some function, that all I have to do is declare a file f and probably give it a name, so a.txt or something like that. And then at the end of the function, I don't have to remember to close that file. The C++ compiler ensures that if the file object has a destructor, that it will be called at the end of the scope. And if any errors happen, that the compiler itself will ensure that the destructor is still called. So that concept of just having a destructor in native classes it's very handy, because it does give you that idea. I actually am encapsulating the notion of a file and not just the resources of it. I'm encapsulating how it's used and so forth. And if that's exactly what we wanted to accomplish with ref classes, which is the managed equivalent of a C++ native class. And ref classes are the classes that any of the languages can use. So if I author a ref class in C++, then C# can make use of that class in Visual Basic. And any class that's authored in C# or VB will come across as a ref class in C++.
Now inside of that ref class, you can be writing native code. In other words, it's not all going to be on the managed heap, right?
So inside of the ref class, all of the contents of a ref class will always be on the managed garbage collected heap, but the functions that are the methods of that class, functions and methods are usually interchanged. As a term, but the functions of that class can make use of native classes. It's a classic abstraction that a ref class can build on top of other APIs, and one of those APIs might be just a C library, or it could be a C++ library, and that gives that library the ability to create functionality that wouldn't otherwise be there. And then the ref class comes across to another language as just a fully managed API. I don't really know what's behind it.
And so, I mean, for example, like in C#, if you have to do a lot of interop, which of course you will need to do in certain cases, right? Because you're just working against native APIs. If you wrote basically an interop class as a ref class that did all that work for you, it would be much more natural for a programmer who knows how to program against native APIs just to provide that class to the UI developers who are writing in C#.
Interop is an interesting thing for me, because if you're thinking about interop in terms of what do you want to interop with, like when it comes to CLR or even Visual Basic 6 or something, what are you trying to interop with? You're trying to interop with something that Visual C++ really omitted. So it could be C code or C++ code or COM code. All of that, it was things that VC was. So it really comes down to interop is trying to use VC technology. And the great thing about interop for using managed code in Visual C++ is that we already understand all of that technology completely because we have header files, we understand COM type libraries and so forth. So there really isn't this notion of having to interpret the world into a managed context. We already understand that whole world completely. And now that we understand the CLR completely, VC is the only language that can actually get to every API that Microsoft shows.
Totally.
Natively.
Now the CLR was probably written in C++, huh?
It was. And so there were some obvious reasons for that.
Sure.
And at some point it needs to bootstrap on something. The libraries, the WinFX and .NET libraries that are included with the CLR are mostly written in managed languages.
Sure.
A large part is C#. But the actual core engine itself and the JIT compiler, those are written in C++. And a large thing is, that they take advantage of the abstractions like exception handling that come with C++ and get a great amount of performance and reliability from that.
Fantastic. So now one of the biggest selling points for managed code, besides the obvious productivity, and that productivity has a lot to do with the tools you get to use as well, but also the fact that you don't have to think about memory. It can take a lot of your mental bandwidth.
Right.
I should say probably implementing memory. You always have to think about memory.
That's right.
But the point I'm trying to make is C++ traditionally well, let's not say traditionally, it's an unsafe language, end of story. What have you guys done in the latest version to make it a little bit harder for developers to write unsafe C++? Because in many cases it's the developer's fault when buffers overflow, etc.
Right.
Could you...
So I certainly take a hard stance on something like that. I think there's developer fault, sure, but I also think there's a language fault too.
Okay.
But there is one thing that we've done, and it's certainly a start to the whole problem, is that we have traditionally when you compile with the /CLR switch, any file that existed today can compile with that, and we really wanted to say you have full compatibility. And if you do compile with a CLR switch and you run into errors, most of those come because there's a higher amount of type checking going on behind the scenes with the compiler, and so they're probably finding bugs in your code.
Okay, could we step? There might be some people who don't really fully understand exactly what that switch does. So if I take a fully native library that I've written in C++, and I do a whack CLR while I'm compiling, what does that mean?
So all that does, if you did nothing else besides compile that with the CLR switch, nothing changes besides the way that the code that's generated operates. And so it's using the JIT compiler to finish compiling it, but otherwise none of the behavior changes. The APIs remain exactly the same, so other DLLs can start using that, using DLL exports, and that's unchanged.
Okay.
So effectively, why would you want to do that if you're just changing how I compile something and going through the JIT compiler? What it does is it enables the code to start using other libraries. So you would never compile with the /CLR switch unless you were starting to think, hey, I want to use the Windows Presentation Foundation, or the XML library in .NET is actually quite good, so I want to start using that. And because it's compiled to the CLR and using the JIT compiler, now my code can start using other things.
Excellent.
So that said, the CLR switch enables the entire scope of what's possible. So we added another switch called CLR Safe, and this basically eliminates all of the language constructs that can't be verified. So when the CLR loads an application, before it actually starts executing functions, it will run through the instructions and see, can these be verified? And that's proving type safety, and it's also looking at, do you have permission to run? If I downloaded this application off the internet, I don't want it to start sending email, and so you'd have permissions like that. So by eliminating all of the unsafe things, we can guarantee that the code will pass the verifier. And so what's unsafe? And it really comes down to pointers. So pointers, when you have a buffer like some array that you write, when I start iterating through this array, say there's 10 things in that, if I have a pointer to it, this now points to the first thing to it, and then if I do p++, this after this executes, the pointer points to the second thing in the array, and I can keep going until I've reached the end. But because there's no way to statically follow or to even dynamically follow where this pointer is going, I can overrun the end of the array and start writing to memory. That's the classic buffer overrun, and we all know that's bad. So pointers themselves are unformed, and so the other thing is things that rely on pointers then become unverifiable as well, and unfortunately that is all of the native classes. Because when you have a class C, such as writing int ab, I have a class that has 8 bytes in it, and so when a function starts writing to, if I had a function like void f, and it took a C star, and in here it wrote C arrow b is equal to 42, then how does this get passed? Well, C star is pointing to the beginning of the class, and so when I get to the B, I have to do a pointer offset. So I add 4 to the to C, and I know that's where B is inside of the class. So when we're working with native classes, we're always doing pointer offsets, and that's just unverifiable. And so ref classes avoid that problem because they actually, when you write something like this, if I put ref in front of this, instead of actually passing C around as a pointer to the beginning of the class, I have an object reference, which is the CLI's way of representing that hat character. So it passes C hat C or something like that. And the class C actually remembers the names A and B. And so instead of generating code that doesn't offset by 4 to get to that B parameter, the actual MSIL will say, I want B, and so it's leaving it up to the JIT compiler to do the pointer arithmetic, and that's past the point that I've determined the code is verifiable.
Excellent.
So that really is somewhat of a I can use C++ for verifiable code, but it does mean that I'm losing a lot of the existing code. Most existing code can't be verified, and but you do keep all of the very cool features in C++ like templates, and those work completely in the CLR safe mode.
Outstanding. Very cool. So you are doing work with the compiler team. I mean, so what changes have you guys made with your compiler output and stuff like that? So your classes, your IL that you generate. I mean, it's probably pretty awesome.
Right. So one thing that's very cool that distinguishes C++ from most of the other languages is that we have a back-end team that optimizes code for just machine code. If we're generating things that don't target the CLR, we have to generate assembly code. And so there's not very much that's different between assembly code and the MSIL code that goes to the CLR. So if we can reapply all of the techniques for optimizing assembly code to MSIL, we can generate better MSIL. And that's helpful for a few reasons. The JIT compiler is constrained by time. If you are running an application and you click some button, you want that button to respond. You don't want the button to sit there while it's optimizing code behind the scenes. And so it has to be responsive. Whereas you hear build times for C++ applications can take hours sometimes. Windows, obviously a big code base, and so they spend a long time optimizing the code. And the more you optimize the code, the better the experience is for the end user. So the VC compiler can optimize MSIL. It can just spend more time, and so things it can do would be like inlining code. We spend a lot of time thinking about what is the right function to inline. So just to explain what inlining is that if I have a simple function that gets some value, and that returns some counter variable or something, that's a very simple function. It doesn't do very much. And so calling that function has an overhead because you have to set up the call frame on the stack and change the program counter and come back. So it's not the benefit of calling this function is not very good because you have an abstraction, which is always good, but you're paying an overhead. So the optimizer can say, well, this doesn't do very much. We can inline it into another function, which means that if I have a function f that simply does something and it calls int x equals get, instead of calling that function, the optimizer would replace that by x equals counter, because that's all this does. And I've basically taken the code from this function and replaced it where I called it.
Sure.
And there's a tension between that. You don't want to inline too much because that causes your code size to grow, and bigger applications take up more memory, and that causes them to run slower. So there's a lot of choices to make. It's actually a very complicated decision to make, and just how much you can inline. So that it kind of explains the JIT doesn't want to spend that time, but our compiler can. And as a result, our compiler can usually generate better MSIL code.
Cool.
So you have some advantage to writing purely managed code in C++ because of that.
Excellent. And I mean, if you're a C++ developer already, why not?
Absolutely.
Why use any other language?
Right.
That's excellent. So what else? What else do we have? What are some of the other core improvements you've made in VC 2005 to the language? So we got CLR, nice, excellent syntax for interoperating with managed code or putting your stuff on the managed heap. We got this slightly safer way of doing things. I mean, more safer anyway. You have the ref classes, which are very cool. What else did you guys do? And it doesn't have to be related to managed code, but just as for a language.
So one thing that actually goes across both managed and native that we did, and it's kind of surprising how much this, we like this on the team, it's the for each construct. And you've seen this in other languages, like VB and C# had this. But being able to write like for each int I in some kind of vector, and just being able to write your code like this, printf the I, it's just so nice. I don't have to figure out what is my end condition, like when I'm writing a for loop, and how do I iterate through that.
Excellent.
And this is completely syntactic sugar. I don't have to have this in the language. I can write it without it. But one thing that really came across is that in managed code with the IEnumerable interface, it really is, it's kind of a drag to always have to set up your loops and then close that down and to possibly call a destructor for the enumerator. So having for each in the language does have a lot of value for writing against the managed APIs. But when we started writing that, we were saying there's no reason why this shouldn't work against STL collections like vector and map. And so we just said, okay, we'll make it work. And as soon as we checked that in and started using it, we were like, this is awesome, and we started using it for our tests, and it's really spread around the team as a great, just a time saver. I don't have to think as hard, and it's not like we want to think less. It's just that we want to think about more important issues than did I set up, iterating through things.
Excellent.
And another thing that was kind of cool I was thinking about is just a very small syntactic thing is that in templates, when I'm creating like a vector of some other template type, so I'll just say type, and it's an int. When you close the brackets here, C++ requires you to put a space there, and the standard does, and that it's something that you learn very quickly, and that's because when you have two angle brackets next to each other, that's a shift operation. So I can say x shift by 2, and that takes the values and shifts the bits over by 2. Okay. So the compiler doesn't want to confuse the shift operation with closing that template. Okay. Well, a lot of times, the shift operation showing up in a template parameter list like this, not very uncommon. So it's one of those just pet peeves a lot of people have. And it's one of those things that the C++ standard is actually thinking about fixing in the next revision, C++ OX. But it's one of those things where you're like, why not just fix it now? And we did that, and we knew that there would be a breaking change when you have some code in here. If you had something like a shift operation inside of the template parameter list, we don't want to confuse that. Sure. And but fixing that would satisfy more people because you're helping the greater amount of people. In that rare case where there's a shift operation, you can just parenthesize that. So I think just a very simple thing like that, it's not a flashy thing, but it does help improve everyone's lives, especially when they're using templates.
Excellent.
Those are things that really excite me.
Cool. So you mentioned templates. What about generics?
So, generics are pretty cool. They're the managed alternative, and really, just to set this up, generics and templates both kind of solve a narrow problem that they want to parameterize functions and types so that when I create a list of, say, integers or a list of strings, I don't have to create different list types for both of those. And both templates and generics solve that problem quite well. They do allow you to parameterize types. The means by which they go about solving that problem are very different, and so as a result, they have different capabilities and powers. And our study of that is like, why would C++ ever need generics? In the end, we're like, well, there's actually quite a few things that generics accomplish that templates don't. And as a result, we thought, well, there is there is some overlap, but there's enough non-overlapping functionality that it does mean that C++ should support both templates and generics.
Excellent.
And for us to do that, we did use the generic keyword just like you would use template. So if you're doing template, and then if you would write class or type name and T So you do the same thing, and I could just, we support templated ref classes, so I can write ref class R and a ref class R. So from the beginning they just operate very much the same way, and here I can have a parameter t, and here I can have a parameter t as well. So where they start to differ is if I wanted to, inside of a template, say call a function on that tf, then what would happen is when I compile this template, I'm actually not type checking it until I instantiate this type with something. So if I did r int, and it came to the point where I substituted int for t, I would see that int doesn't have a function f, and so that can't compile. It'd give you a compiler error when I instantiated this type. But so getting that error r of int makes sense at compile time, because templates are fundamentally a compile time feature. Generics are a runtime feature. The CLR provides a lot of the functionality that make generics work.
Okay.
And so if I create a generic in one library, I want to use it in another library, then I have to make sure that it type checks in my library before the other library can use it. And so if I tried inside of the generic to do something where I ended up having a call to function f, then inside of the generic code itself I would get an error, because every type in the world does not have a function f. And so I have to provide some way of telling the compiler and the CLR that this function does indeed have a function f. And that's where constraints come in. And so in this place right here in the syntax, we would write something called a constraint, where you write where, and and you take the type parameter t, and you say that type parameter implements an interface, or it has a constructor, or that it's a ref class. And so I might have a function, I, or interface I, that says that I has the function f. So any type parameter t that I use for this template is going to have that function f. And so when I start compiling this code, the compiler is going to say, okay, it does have an f. Okay. And that kind of makes a difference when I go and then try and do r of int. Int doesn't implement the interface I. So instead of getting the error that int doesn't have a function f, you're going to get another error that says that int doesn't implement the interface I instead. And so you get something like the means by which, how would I solve this problem? With a generic, I would go find another type that does implement I. With a template, I could go back and fix the class to add a function f or something like that. Or with templates, there's another feature that generics don't have, which is specialization. I could go specialize that template for my type that might not work with the other template.
Interesting.
So there's quite a lot there, but generics really have the ability to work across libraries, across those assembly boundaries, and templates don't. I guess templates are a compile time feature only.
Understood. Very cool. Well, what else do we have here? What else do you want to talk about?
Let's see. I guess the interesting thing is, where is this all going?
Excellent.
So C++, CLI really, I've been getting a lot of great feedback, so I have to thank everyone who's been sending that to me about how useful this is, that they really feel like they can start using .NET and the CLR because of the new syntax. And we're just going to have to keep focusing on what's next. There's a lot of new libraries that are building even better technologies. the Windows Presentation Foundation has XAML, and so how do we integrate XAML code into C++ is something that we're really focused on.
Interesting.
So there are definitely language questions involved there. But what I really spend a lot of my time about thinking is the developer experience with the compiler. It's really fun to think about inventing new language constructs, and I have to admit that this is by far the dream job I could ever get. But right now, what I hear a lot is the compiler is not fast enough, or I really like the fast linking experience that unmanaged code has, and really bringing that experience forward to the managed coding experience, so that you're not giving up that developer experience when you start using .NET technologies. Those are things that I'm thinking about. So they're really kind of low level. I just want it to work like it used to work, kind of things.
Excellent.
And that's where a lot of my time is going.
And I know that we can't really talk very much about this, but it is public knowledge because it was talked about at a non-NDA conference recently. Herb Sutter on your team and guys are working on an interesting solution to make it easier for people to write concurrent code.
That's right.
By actually adding it to the language.
Yep, and
that's exciting.
It really is, and I think what Herb's doing is really cool. He's really spending a lot of time studying concurrency, and the way he thinks about like the abstractions we have today with locks and mutexes and so forth is really kind of the assembly code for concurrency, and I really want a higher level language idea, and so that's certainly coming forward as a kind of an incubation project that we're developing, and hopefully that's going to come soon.
Very cool. Now we're going to continue the C++ tour over the next coming several months. Next will be probably checking out the Phoenix compiler. You guys are doing amazing work. It's an extensible compiler.
That's true.
Which is very cool. And we'll keep checking in on C++ for sure. It's it's the most widely used language in the world. And it's not going anywhere except for evolving nicely to fit into really the future of programming, which really is managed, right? It really is.
For Windows, that's definitely
Windows.
sure.
Totally.
And I think another thing to say in that vein is that C++ is one of the widely used languages because it's supported on more platforms than just Windows.
Yeah.
And all of the work we're doing here is to make that remain an effective approach. Is that you can write code that's cross-platform, and this still helps you do that.
Fantastic. Well, thank you for your time, Brandon.
Well, thank you.
All right, we'll talk to you again soon.
All right.